Continuing on in section 3.3, this is 3.3 part 2, we're talking about functions, and in particular their graphs. So we've already said, like, is it a function? That's the vertical line test. Now we're saying that it is a function. We're going to talk about specific properties of functions. One of the best properties when we look at a function, one thing that we almost always notice are the following things. Is it going up or increasing? Is it going down or decreasing? Or is it staying the same? So there's only three things a graph can be doing over an interval, and that's saying between values x1 and x2. Either the value of f of x2 is bigger than f of x1, means it's increasing, right? The value of f of x1 is bigger than f of x2, means it's going down or decreasing. And if they're the same, that means that it could have had a little loop right there. Maybe that's not the best way to describe it, because it's saying that for all the x inside that interval, they have to stay the same. So it could do one of these things, though. Go up, go down, or stay the same. That's really it. And we just write it technically in this way. So I won't spend a lot of time on this slide. You, of course, can open the slide and look at this too, to say here's the exact things. You're either increasing, decreasing, or you are constant. So let's look at an example of this crazy graph right here. And let's try to find, and now notice it doesn't have any arrows on the end, so this is the whole entire graph right here. It doesn't have those arrows, it's not going on to infinity. And if we want to ask some other questions like the domain and the range, that might be interesting. The domain here is going to be -6 to 6, and the range is going to be from y equals -4 up until 4. So think about that one for a while. Or maybe just think about that one for a moment. But let's actually answer the questions. So where's the function increasing? Hopefully you can look and you can see, well, it's a low point right there, and it's increasing all the way up to there. So I have to write that in an interval form. There it is. And what do we have? That is from -4 to 0. Notice, we only look at the x. We read this like a book, because x moves from left to right. So we read it like a book from left to right. We do not concern ourselves with the y values when we're talking about where the function is increasing. We're looking at the x interval. And the way to write this is -4, 0. That describes an interval right now. It does not describe an ordered pair. I know that can be confusing, but that's just the way it goes. All right, so let's continue. That was where is it increasing? Now let's see where is it decreasing. Now you might notice it's actually decreasing in two spots. One spot is between those two lines, and the second spot, so between -6 and -4, but it's also decreasing somewhere else, and that's going to be between 3 and 6. Now I know the values are between 4 and 1, but remember we're focused on the x values, and that's going to be from 3 to 6. So we have two values there where the function is decreasing. We just focus on the x locations, right, or the x intervals. That's what we care about. And finally, we're going to have to ask, where is it constant? And you can see it's constant at the value y equals 4, but it's constant from x equals 0 to 1, 2, 3. So let's draw that line. We see it's between 0 and 3, and we can write it this way, 0, 3. Maybe I didn't spend enough time on that one. There it is again. So what happens if a function, so now questions to ask yourself that could be important when we look at graphs is what happens if a function is decreasing until a point and then starts increasing? What does that mean? Whoops. I don't know what happened there. What does that mean? What could happen then? Oh, I thought my pen would point, but it's doing something. Oops. Well, I'll keep on going. So if a function is decreasing, like that, and then starts increasing, maybe you can see right there, I just made sort of like a V shape or a U shape. Similarly, or I should say vice versa, if it starts increasing and then decreases, you've reached some sort of, it's almost like you made a little mountain right there. So you have a valley and a peak. Well, let's think about what that means. And we'll think about it in the context of an application problem. So here's a problem. I can't do this in my head. I'd pull out a calculator and do it. And I'm just going to look at different values where my obvious goal is to try to find the minimal average cost. Since this is a cost, and maybe if it's my business, I want it to be the cheapest possible cost to build these things. And it's all based on manufacturing a certain number of computers per day given this function. So if I were to do 30 computers in a day, I would just do what? Plug in 30 wherever I see an X up there. And I get the number $1,351.54 per computer is how much it costs to manufacture these things. So I'm like, okay, well, there's a value. Is that the smallest? Is that the minimal one? I have no way of knowing because I don't know any other values. So I could also plug in a 40. Well, I'm like, well, 40 is better. I'll do 40 instead of doing 30. Right? That could be a better value because it's $1,232.97. But I'm not sure yet. Maybe it keeps on getting lower and lower. So I plug in 50. Well, that's a higher value. So already I can see that I'm going down and then coming back up. So somewhere in between there, if you thought about the last slide, you might notice that we'll have reached a minimum point, a valley. We want to find that point in the valley because that's going to be our lowest point. So what I would do then is I would graph the whole function on a graphing calculator, and I would actually be able to go in there and find the minimal value. And in this case, our minimal value is x equals 41. It's not exactly 40. It's somewhere between 40 and 50. But it could have been anywhere between 30 and 50. I wasn't exactly sure where I was going to hit that minimum. So x equals 41 is the production level that minimizes our average cost. So let's go on and actually talk about this in particular. What we just found was a local minimum. That was important to us. It was a place that was the lowest on our graph for a certain interval. Okay? We also could have a local maximum. So local minimums are basically the low point of a valley. Local maximums are the high point of a peak or a mountain. And like I said, we can look at an example right here with a function, and we can see these things. So to find, I could say, can anyone, of course you can't talk to me, to find a local maximum, hopefully you can see, now these are infinities, so we don't compare those. We look at the little tiny little mountains right there. So there is a local maximum. And the question though is saying, what number does f have a local maximum? It has a local maximum at that point 1, 2. But that means that we care about the x value of the local maximum. It says at what number or where does it have the local maximum? It has it when x equals 1. Instead, if it says what is the local maximum, then it's going to be 2 right there. Now, what are the local maxima? So this is what it's saying. It's saying the local maximum value is 2. Do you see the difference? So that's going to be y equals 2. I could have put that down 2 to be more specific. So we found that guy. Let's move on. At what number does it have a local minimum? Well, there's actually 2 of them. There's one at x equals -1 and x equals 3. So already you should know that we care about the x values there. And now, if we move on, we find the local minima, and they're going to be at 1 and 0. So we might want to put down ordered pairs here, -1, 1, and 3, 0, because that gives us more information. But this is certainly useful in following the rules of what it's asking. Now finally we have to say, what are the intervals that it's increasing on? Well, remember last time we had this closed off boundaries. It didn't go to infinity, but now infinity is included. So we say intervals on which f is increasing. Well, you can see it's going up between there and there, so we'd write that only the x's, right? 1 to -1 to 1. But it's also going from there forever. So for that one, we have to make sure we put infinity inside of it. So we have the 2 areas where it's increasing, and that's -1, 1, and 3 to infinity. And now for decreasing, we're going to have just our opposite guys. Remember, we read left, even though this arrow is going up to the left, we read from left to right. So we have all the way from -infinity down to there, and from 1 to 3. Because remember, we just care about the x's. So those are our intervals. We have no places where we were constant. So we have, we just found a local maximum and local minimum, but we also can talk about something called an absolute maximum or an absolute oh, shoot, that should be a minimum. Absolute minimum. Excuse me, that is wrong. This is right, f of x greater than f of c, but this is wrong. Absolute minimum should be the word right there. And I'm not going to stop the whole tape just for one little mistake like that. I'll make plenty of mistakes. But we can find an absolute one if it's the smallest out of everything in the whole graph. So if we go back to this guy, this is the absolute minimum of the whole graph because there's nothing lower than it anywhere. So the location of the absolute minimum is x equals 3. The value of the absolute minimum is 0. Now our last bit of discussion here is on average rate of change. This is the calculation for it. And what I want to point out is that this is not a new idea at all. If you did anything with lines in your whole life, which I'm sure if you're in this class you should have, then you know that this looks just like the equation of slope, right? It's really saying y2 minus y1 over x2 minus x1. That's what change in y over change in x equals. Wow, so this is just slope. And instead it's saying though that we can do an average rate of change even if our function is not a line, because we can find how things change between 2 points. So if we want to find how we change from 1 to 5, and we're going to do this kind of quickly, then we just plug in those values, right? We say, well, here's a graph of this whole thing. So I have all the values on there for you to look at, and you can see f of 5, we can see there's our calculations, it's just rise over run, and we have a slope or average rate of change of 18. But now the question is, what is this the slope of? It's really the slope of a line, right? And so this is called the secant line. It's a line that touches the graph in exactly these 2 points, the point 1, 3 and 5, 75. So you might remember these sort of things from these. This is our review. I'm just going to go through it quickly because we're running out of time here on this presentation. But you might remember this this point slope equation, and so we want to get y equals mx plus b. We get that, and we have our actual line is the green thing, and we can see that slope. Now we could also do, so that's the average rate of change is 18. It means that for every one step you move to the right, you move up 18. So it's 18 y's per x. That's really what it's saying, or like 18 miles per hour. It's a rate of change, a speed in effect. So now if we do this from 1 to 7, you might have remembered it should be a steeper line. So a steeper line represents itself as a higher number. 24 is bigger than 18. If we find the equation of this line, we'll see that, it is a steeper line. Now you notice it also does a better job of approximating this curve at that point. All right, it approximates it better by going up right there. So it approximates better over this range. It's not as good at approximating 3, right? But it's good at approximating it sort of right here. You can tell that as this graph grows, it's going to do a poor job of approximating it going forward. That's something we want to remember about lines. So let's see how this is used in the real world. So here's our September flood. And I want to talk about graphs, right? So right here we talk about increasing and decreasing. If you looked at this graph, you're like, oh, phew, on September 5th during the day, we missed having a flood. Isn't that good? Because I remember at 7 is where things get bad for us. But in actuality, what happened? It didn't stop. It went down right there, but then it started going up again, and in fact, it did flood as of basically midnight on September the 7th. So that was not good news for us. It must have started raining again right there, and something happened. But one thing we did learn, and we can use math for, is we can look at this graph and say, when it rains really hard, this is how quickly, using this line, using this slope or average rate of change, this is how quickly the water is increasing per hour, right? Or the height of the creek is increasing per hour. It's increasing over 5 feet per 8 hours. That's what it is over this full range right there. We could do a per hour basis too. So I could actually do that as a slope. But this is a slope over 8 hours. And if I want to compare that, because it's the same thing, I can say, wow, it really was increasing at that same level when it started raining hard again. So it happened a second time. Now you might say, well, what if it continued raining at that rate? Well, that would have been really, really bad. See how high that would have gone? It's like completely off the charts. It would have been like 14 feet high or like double the height of the creek. That would have been really horrible. And luckily, it did not happen, right? It went down and stopped raining. But it's an example of how lines can be used to approximate things that are not lines. But you have to understand the context they're used in and the assumptions that are used to make them work. So that will be an important discussion for us to certainly have at the beach. I hope you enjoyed this section. We'll talk soon.